right, good morning class. Welcome back. We are on day 2 of the Pythagorean theorem, the thing we just talked about yesterday. And 12.1 is broken up into 2 pieces because today we're going to talk about the famous box problem. Alright, usually this problem involves a box and something you want to ship. Okay, so I have a word problem here that has the box problem and a piece that we want to ship. Okay, and it's kind of hard to see what's going on with this box problem. So let me do a little demonstration for you on what this box problem involves so you can get a visual with what's happening. Alright, so you're going to have to use your imagination and pretend that you have this strange friend. Okay, and this friend is kind of strange because this friend would like you to send them a toothpick in a toothpick box. They want you to ship a toothpick inside of a toothpick box. And the reason why this is such a strange request is because your friend has asked you to send only one toothpick, and they would like you to send the largest toothpick that you can fit inside the box. Alright, the largest toothpick that you can fit. Okay, so let's take a look at some samples. Let's say we're going to send a toothpick, and I have our very first toothpick that we are going to send. And if you put this toothpick in the box, it'll fit in there very nicely in the bottom, and that toothpick does fit, not a problem at all, but it is not the longest toothpick that you can send in the box. Alright, there is actually a longer toothpick. If we actually took the toothpick and went diagonal with it, we could ship a larger toothpick. Alright, so let's take a look at this. Instead of this toothpick, we're going to go with a different size, and we are going to actually send a toothpick larger than that. That'll fit in there diagonal. Alright, now isn't that nice? It fits in there diagonally. It is a larger toothpick than the one we had in there before. But we are not done. No, we are not done, because there is even a larger toothpick that'll fit in there. Believe it or not, there is a larger toothpick that'll fit, because this one is lying flat on the bottom diagonally. But if we actually got a toothpick to fit so that part of it stands up on the top diagonally and part of it will fit on the bottom, then we would even get a bigger toothpick to fit inside of this box. So I'm going to show a bigger one that'll fit. The third one that we would actually send is one that would fit diagonally, but it also fits sideways. Okay, it is diagonal inside the box, but it also fits in there sideways. Okay, I'll see if I can get a visual on this. Okay, kind of, sort of. You can see that it fits sideways. It's hard to really show. I wish I had a clear box to show you. But that's what we want. We want to find the largest toothpick or the largest object that'll fit in the box by going diagonally like this, but having one end be up at the top and the other end be at the bottom, because that would be the largest object that we could send in a box. Alright, so with that nice demonstration in mind, and with the help of my toothpick and my toothpick box, we're going to jump to this word problem and we're going to solve this. Okay? Now, with this word problem, we're doing the same exact steps we did yesterday, same thing, but we're just going to do it twice. Alright, we're just going to take the Pythagorean theorem and we're just going to solve that for 2 triangles instead of 1 triangle. Okay, so let's check out what we have here. We have this box, and it is used for shipping narrow copper tubes. The box measures 6 meters by 3 meters by 4 meters. Okay, and I have that labeled here for us. And we want to know what is the length of the longest tube that will fit in the box. Okay, so this tube is represented by diagonal AB, and just like in the toothpick box, it goes diagonally from corner to corner, and it also has one end on the top and one end on the bottom. So that is our largest size object that we would be able to fit inside the box. Okay, so how we start solving this is we actually have two triangles here that we need to solve for. Okay, so let me outline this. I'm going to start with the green triangle, and the first triangle we have is this one on the bottom. Okay, we have a bottom triangle, and our bottom triangle will be green. All right, and it's going to look just like that. Okay, our bottom triangle. And the second triangle we're going to solve for. So first we're going to find the missing length of the first triangle, the green one, and then we're going to use that to help us find the length of the second triangle, which will give us our answer. And that second triangle is the purple triangle. Okay, so we end up with two triangles here that we need to solve for. That's why I said we're going to take the Pythagorean theorem and we're going to solve for it twice, because we have two different triangles we're trying to find, two triangles we're trying to solve for. Okay, so we just did step number one. And step number one was to pull out the two triangles. Okay, we found this triangle and we found this one, the two pieces that we need. All right. Step number two, we're going to do the first Pythagorean theorem to the first triangle, and we're going to find the length of the bottom diagonal. Okay, in the bottom diagonal, what I mean by that is this diagonal right here, this one going across the bottom of the box. We need to know what this length is. Okay, and we're going to use the Pythagorean theorem to do that. So our first triangle, our green triangle, down here on the bottom, this is a right triangle because this is a right angle. Okay, and since this side is 3, we know that this side over here would also be 3. And we already know that the bottom width of the box is 6. So we have both the legs of the triangle, and we want to find the hypotenuse, the side that's opposite of the right angle. Okay, so looking at our Pythagorean theorem, we go a squared plus b squared equals c squared. Okay, and that's exactly what we're going to find and what we're going to work out. All right, so that's our Pythagorean theorem. Now we're just going to plug in these numbers into the theorem. All right, we have our side A and we have our side B, and this diagonal is C. That's what we're trying to find. Okay, so we're going to put those numbers in. We're going to say 3 to the power of 2, because that's my A, plus 6 to the power of 2 equals C to the power of 2. All right? So when I do that, I'm going to do the math on this just like we did yesterday. And we're going to have 9 plus 36 equals 45. Okay, and just like yesterday, we're not done yet. 45 is not our answer because 45 is c to the power of 2. Okay, and we want c by itself. So if we take the square root of 45, it's going to give us a very long number. It's actually going to give us an irrational number. So we're going to round that, and we're just going to call it 6.7. Okay, if we found the square root of 45, the closest number we'd get to it is 6.7. Okay, so 6.7 is the length of this diagonal right here. All right, so we just worked out the bottom triangle, our green triangle. I'll circle it in green to show that that's the triangle we worked out. And we found this missing side right here. Okay? And we needed that missing side because we're going to use this 6.7 to help us find out the length of this diagonal. All right, so we're jumping over to step number 3. And step number 3 is to find the length of the side diagonal. Okay, I call it the side diagonal because this diagonal goes from one side of the box to the other side, our side diagonal. Okay, so we already know this bottom piece here is 6.7. There's our right angle. Okay, so we have one of the legs is 6.7. The other leg is going to be 4 because we have 4 over here, so that's going to make this side 4. All right, so we have A, we have B, and now we just need to find outside C, which is the hypotenuse again, just like we did on the first triangle. All right, so our purple triangle, when we work this out, okay, let's plug these numbers in here. We are going to have 4 squared, because that's my A, plus 6.7 squared, because that's my B, and that's going to equal C squared. All right, and I'm going to work out the math, and we get 16 plus, and 6.7 squared, we already figured that out because that was our 45. Okay, we just took the square root of 45 and we got 6.7. So I'm going to use 45 again because we already know that that's the number that, that we used. Okay, 45 equals c squared. Okay, add those two up, we get c squared equals 61. All right, now we're not done yet. 61 is not our answer. So we need to take the square root of 61, and it is also an irrational number. It's going to get us a very long number that will not end. So we're going to have to round this one also, and we're going to call it 7.8. All right, so the longest, that tells us the longest piece of copper tube that we could send in this box is 7.8 meters long, all right, which is this length of the diagonal going from the top to the bottom of the box. All right, and that was our purple triangle, so I'm going to circle that in purple just because I have these colorful pens here, and they are nice to use. All right, so that is my purple triangle. That is it for today. You're just going to have some problems like that on your homework. The classic box problem, where you have to ship some sort of object in there and make it the largest object you can. All right? Same thing we did yesterday. Pythagorean theorem just 2 times.